Cool, cool. We're back. It's chapter 7, which continues our study of trigonometry. Section 7.1, we're going to learn about inverse sine, cosine, tangent functions. Okay, so the goal is to define and be able to find values of the inverse sine, inverse cosine, inverse tangent functions, and then we're going to use properties of these functions to solve various equations. So the sine function is graphed here. This is just your plain old normal y equals sine x. Now, does this have an inverse? So the question we ask is it 1-to-1? And we pretty quickly see no, it absolutely isn't, right? It fails the horizontal line test rather spectacularly. When we draw horizontal lines, either it misses the graph completely, which is fine, or it's going to hit it infinitely many times. It very much fails the horizontal line test. But, and we hinted at this back in chapter 5, if a function fails the horizontal line test, what you can do is you can restrict the domain so that it now passes it. Now, our goal is to restrict the domain to a small piece of the real number line where we want to capture as much behavior of the sine function as we can while still making it pass the horizontal line test. So what we would do is we would either pick an interval where it goes from the maximum all the way down to the minimum. If we went any further, we would start to fail the horizontal line test down here. Okay, but what we'll have done is we'll have found all possible values of the sine function from its maximum all the way down to its minimum. The standard, however, is to go from its minimum at -π/2 to its maximum at π/2. And if I cut off the domain down here at the bottom now to just be from -π/2 to π/2, now the resulting graph does pass the horizontal line test. Okay, so sine function, no, it's not 1-to-1, so we restrict the domain, and now it is. But bear in mind that this function is not exactly the sine curve we're used to. It's the sine curve with a restricted domain. Its domain is only from -π/2 to π/2. But then we can invert it. So we define the inverse sine function, okay, to be the inverse of this function. Specifically, okay, the only thing that we can plug into the function we're inverting over here, so y needs to be in the domain, not of the general sine function, but of the restricted sine function, which means y needs to be between plus and minus π/2. And then we have an invertible function, and then we define the inverse sine function, also called the arc sine function. That tends to be how I say it, arc sine. And it may also be written instead of sine with this exponent of -1, which we have gotten used to as an inverse function. It's sometimes written as arc sine of x. Sometimes I might write it like that if I want to avoid possible confusion with an exponent of -1. Okay, remember that this notation, this -1 above the sign, doesn't mean an exponent of -1. It specifically means the inverse sine function. Okay, but bear in mind, it's only the inverse function of the restricted sine function, meaning y has to be between -π/2 and π/2, which means that the range of the inverse sine function is the domain of its inverse. But remember, it's not inverting the normal sine function, it's inverting the restricted sine function. So the range of arc sine is -π/2 to π/2, the domain of that restricted sine function. And what's the domain of the inverse sine function? It will be the range of the restricted sine function, but we specifically built that restricted sine function to capture the entire range. It went from a minimum all the way to a maximum. It went all the way from -1 to 1. So that is the domain of the arc sine function, the range of the restricted sine function that it's inverting. And that's summarized down here at the bottom. Okay, we have y is arc sine of x. The thing we plug in, the domain, is between -1 and +1. The thing we get out, the range, is between plus and minus π/2. The graph of it is given here. It's just the graph of the restricted sine function, which is in red, and you reflect it across the line y equals x, and that gives you the arc sine function. We don't graph this function very much. Point is, it's there. Okay. So for example, find the exact value of arc sine of -1. So ask yourself, what was the domain The domain of the arcsine function was from -1 to 1, so this is in the domain. Okay, so it's a reasonable question to ask. Arcsine of -1, what it really means is theta is an angle. It's the arcsine of -1, and what it means is theta is an angle whose sine is 1. That's what you should really think when you see this. Theta is an angle whose sine is -1. So what is an angle whose sine is 1? Sorry, -1. What is an angle whose sine is -1? But more specifically, because there are actually infinitely many such angles, what is the angle between plus or minus pi over 2? So if I look at the unit circle, okay, I want the sine of the angle to be -1. I want the y coordinate on the unit circle to be -1. There's only one point that does it. It's down there. What's the angle that points straight down? Well, we could do, for example, 3 pi over 2, but that's not a legit answer here, because looking back up towards the top, the only angles we're going to consider are between -pi over 2 and pi over 2. Specifically, it's got to be somewhere in this range, okay, between -pi over 2 and +pi over 2. What angle points to the point on the unit circle whose y-coordinate is -1? -pi over 2. Pointing straight down, the angle is -pi over 2. Okay, I'm going to clear out my marks because it's going to answer the question here with nice fancy writing. So again, we set theta to be the angle whose sine is -1, specifically the angle between plus or minus pi over 2. So the sine of theta must be -1. Okay, and if we look at the table of values we know, what's an angle whose sine is -1? Specifically between positive and negative pi over 2. The only one whose sine is -1 is right here at -pi over 2. So the only angle that we're considering whose sine is -1 is pi over 2. And as I remarked on the previous slide, there are other angles whose sine is -1, but we're only looking for an angle between plus or minus pi over 2. And this is just another picture of the sine curve. Okay. Just pointing out again that the angle in the restricted domain whose sine is -1 is -pi over 2. So let's do another. Find the exact value of arcsine of √3 over 2. So again, if I just call this theta, and I'm using the letter theta because arcsine of √3 over 2 specifically means the angle between plus or minus pi over 2 whose sine is that input of √3 over 2. So if I set theta to be the arcsine of √3 over 2, I'm asking the sine of theta must be √3 over 2. You can think of this by definition, or you can think of it as taking the sine of both sides, a technique that we'll see later on in this section. So what's an angle whose sine is √3 over 2? Well, the only angle in between plus or minus pi over 2 whose sine is √3 over 2 is pi over 3. Sorry, I'll go back because I want to draw a picture of this. So here's the unit circle. I want an angle whose sine is √3 over 2. So I want the y-coordinate of the point on the circle to be √3 over 2. So I'm going to draw the line y equals √3 over 2, and it's at about here. Okay. It's a horizontal line, and it's about there. Notice it intersects the circle in 2 different places. So how many angles are there whose sine is √3 over 2? Infinitely many, and even more so in one full rotation of the circle, there's actually 2 such angles. There's that one, and there's this one over here. And then, of course, I can go around multiple times. I can go backwards, whatever. But we are specifically looking for the angle in between plus or minus pi over 2. So I'm only looking in quadrant 4 and quadrant 1, which means I'm looking for this angle right here. Okay, and that angle is pi over 3. Okay. So find an approximate value for each of the following. Okay, and notice it says express the answer in radians. Remember, arcsine of 1/3 specifically means an angle whose sine is 1/3. So we really can't do this any other way than by using a calculator. Just make sure you're in radians mode. If the answer should be in radians, make sure you're in radians mode. If you're okay using degrees in a particular problem, that's fine. But, as always, just know which mode you're in. Okay, so if you just punch that into your calculator, you should get that the arcsine of 1/3 is 0.34 radians. And what if you try arcsine of -1/4? About -0.25. Okay. There are very few values for which we're going to be able to say what the arcsine is exactly. Normally, we'll just approximate it. Okay, so just to summarize what we did in this video, the sine curve is not 1-to-1. Because it fails the horizontal line test, oops, sorry about that, pretty spectacularly. Okay, most horizontal lines will intersect it infinitely many times. But if we start at the minimum of -π/2, -1, and just go until it hits the maximum of π/2, 1, now this is 1-to-1. So it has an inverse. And we call that inverse x is the arcsine of y. And remember that inverse functions swap domain and range to the original. So this restricted function has domain from -π/2 to π/2, which means the range of arcsine is from -π/2 to π/2. And the domain of the inverse function will be the range of the original, and the restricted sine function goes from -1 to 1. So the domain of arcsine is -1 to 1. Okay. So what happens a lot, just to let you know, is someone might make a pretty understandable mistake as part of a problem. They make a silly computational error of saying, I don't know, 2 + 3 = 6. Something totally understandable that we all do from time to time. But what it leads to them doing at a certain stage in the problem is writing something down like the arcsine of 4. Okay. Now imagine you are staring at someone who has written down the arcsine of 4. This represents an angle whose sine is 4. And that's ridiculous. And you go, ha 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 ha, what a silly person. There is no such thing. And you laugh at them. Okay. There is no angle whose sine is 4 because sine is trapped between ± or -1. So as soon as you write down something like arcsine of 4, you know you've made a mistake. It just doesn't mean anything. Okay, so we're going to come back in the next video, and having defined here the inverse of sine, in the next video we'll come back and talk about the inverse of cosine.